Today we're going to start talking about the properties of gases and to begin with kinetic molecular theory. So you could just follow along in your packet and fill in notes as we go. So kinetic molecular theory is basically what we're going to refer back to every time we want to talk about how a gas is behaving. So when we talk about things like, well, how come gases feel pressure, or what happens when we change the temperature, what happens to the volume, the velocity, which is the speed, the frequency, which is like the amount of times we'll refer to gas particles colliding, or force of collisions. We're going to come back and talk about this idea of kinetic molecular theory. So let's get into it. What is kinetic molecular theory? Before we really start talking about it, though, I want you to visualize what a gas particles look like. So here's a container of gas particles. There's some red, some blue. There's really no reason for the different colors, but just to differentiate that one's one gas and one's another. If you notice, the particles are just moving around. It's kind of a random direction. There's no set path that they have to go. Sometimes they bounce into each other. Sometimes they bounce into the walls of the container. But either way, at some point, the particles do collide. So when we start to look at kinetic molecular theory, I just want you to keep in mind this idea. This is this picture of gas molecules in a container. So here are the postulates, we could say, of kinetic molecular theory. So gases are composed of particles that are in constant random motion. Those particles in the gas box that we just showed you are constantly moving. None are sitting still. And they basically will continue moving in a straight line. Like if you notice, they were not traveling in curvy paths. It was a straight line until they bounced off each other or the walls of the container. Second thing we need to know is there's a lot of distance between the particles. So typically we say that the volume of gas particle can be ignored because there's more space between them than the amount of space they actually take up. The gas particles are not attracted to each other. They're not repelled by each other. It's not like they come near each other and then boom, like they have to be on each other like glue. And it's not like they come near each other and you see like extreme repulsion. The gas particles will collide with the walls of the container, and you will get some type of transfer of energy. We say that in this case, the energy can't be created or destroyed. We know that energy, once it bounces off the walls of the container into each other, will be transferred to another particle if it goes into another gas particle. So we say this word elastic, and you'll see that come up in different regions questions, that energy gets transferred from one particle to another, but no energy is ever lost. It's not like they bounce into each other and then the gas particles fall to the ground. The energy will always be transferred. So we use this acronym SCAN to help us remember the different ideas about what's going on inside a box, or if we were to think about what's happening to the particles of a gas molecules. So S stands for straight, constant, random motion. The particles are traveling straight, constant, random lines. When the particles collide, collisions are elastic. Elastic, remember, just means that energy is going to be transferred. We're not losing energy. We assume no attractive or repulsive forces, and the particles have negligible volume. Negligible pretty much means like almost no volume. Gas particles take up very, very little space. There's more space between them because they're separated by great distances than the amount of space they actually take up. So SCAN is a nice little acronym. You know, I love acronyms to help us remember what's happening inside the walls of a container when we have gas present. And we're often asked in Regents questions to try to recall the postulates of kinetic molecular theory. So just want to talk a little bit about pressure because it's something that's come up a little bit, but we haven't really talked about why do we feel pressure. So what is pressure? Pressure is the result of collisions of the molecules, the gas particles, when they hit the side of the container. So you have these gas particles bouncing around, and then when they hit the container, the collisions that they have with the wall of the container cause it to exert a pressure. If you have the particles having more collisions, they're going to hit the walls of the container more often. There'll be more pressure. We also know that pressure goes from areas of greater concentration to lesser concentration. So for instance, if you increase the pressure, and let's say your tire, it would expand to fill the space around it. We measure pressure in units of atmospheres or kilopascals. Atmospheres are abbreviated. We have the unit ATM, and kilopascals are kPa. Remember to check out Table D on your front of your reference table. It has all of our units. Handy dandy reference table. Okay, so that's pressure. Let's talk a little bit about temperature. Temperature has a direct relationship with kinetic energy. Temperature actually is a direct measure of the average kinetic energy. So if you increase the temperature, the particles are going to be moving faster. They have more kinetic energy. If you make the temperature colder or lower, the particles are going to be moving slower. So there is a direct, remember direct, we said that as one goes up, the other one goes up. That's direct relationship. So if we increase the temperature, the particles are going to be moving around lots, like faster. And if we decrease the temperature, the particles are going to move slower. All right. As far as where we could find values for standard temperature and pressure, that's on the very, very front of your reference table. So for honors guys, we've talked about the fact that 22.4 liters equals a mole. That's true at standard temperature and pressure. For our regents guys, I want you to know this table is here for us, the very, very front of the reference table. Standard pressure is 1 atmosphere or 101 kPa. You see here ATM is showing you that ATM is atmospheres. They're showing you kPa is kilopascals. So it's not like you have to memorize them if you forget them. Standard temperature is 0 degrees Celsius. It tells you here degrees Celsius and 273 Kelvin. So that's all there for you. You don't have to memorize it. And we're going to be using that a lot over the next few days. So keep that in mind. Anytime a question says, oh, we're at SGP, let's go to table A. Also, I know we're super smart and we wouldn't forget this, but just in case you did, remember that we're going to need to be converting from Celsius to Kelvin and back and forth. For the gas law problems that we're going to be doing, everything has to be in Kelvin. That's right. Everything has to be in Kelvin. So when we're talking about conversions, remember on the back of the reference table, table T, you have Kelvin equals Celsius plus 273. Don't forget that it's there. Don't assume that you know how to do it because a lot of times we make mistakes. Please just plug it right into the equation. And then that way we know that when we're using temperature in a gas law problem, we will always have it in the Kelvin temperature.